Okay, welcome back to the Algebra 2 final exam review. In this video, we're going to cover section 13, where we're going to simplify uh, just adding, subtracting some radicals together. And the one of the big properties that we're going to really use in this video is that the square root of a times b is equal to the square root of a times the square root of b. And we see this when we're doing a factor tree. So, for example, if we had something like 18 and we make a factor tree with it, we can break this up as 9 times 2. And 2 is prime, so we can leave it alone. And then we try to break up 9 as much as we can, and we get 3 and 3. And when we do that, we could say that 18 is equal to 2 times 3 times 3. Which makes sense because 3 times 3 is 9, 9 times 2 is 18. So this is called a prime factorization. Well, fortunately, prime factorization still works when we're doing it inside of a square root. So if we're doing the square root of 18, this is the same thing as the square root of 9 times the square root of 2. And the square root of 9 can be broken up as the square root of 3 times the square root of 3. So the square root of 18 is the same thing as the square root of 2 times the square root of 3 times the square root of 3. However, we have to take this a step further to simplify it. We gather up all of our pairs of square roots. So we have 2 square roots of 3 here, and this gives us just a 3, because square root of 3 times square root of 3 is just 3. And so what we really say is that this is equal to 3 square root of 2. And so this is how we can simplify square roots. However, we don't actually have to make a full factor tree like this. In fact, if we just break this up, if I repeat it over here, if we instead ask ourselves, what's the biggest perfect square that we can divide 18 by? Remember that our perfect squares are numbers like this. We have the square root of 4 is equal to 2, the square root of 9 is equal to 3, the square root of 16 is equal to 4, and so on and so forth. And we can keep making a list like that. The square root of 18 is, if we divide 18 by the biggest perfect square we can, which is 9, the square root of 9 and the square root of 2 can actually be simplified from here. The square root of 9 is just the same thing as 3. And so we can actually skip the step of making a longer factor tree like this if we divide by the biggest perfect square we possibly can. And so in class, we have those sheets that we made, the common exponents. And if you know how to read it correctly, it gives you all of your perfect squares. And it actually makes making factor trees pretty simple. We just divide by the biggest perfect square we possibly can. And it simplifies really nicely with just 2 branches. And with our perfect square, like in this one, the square root of 9 is just 3. And we can write this as the square root of 3 times 2 and bypass making a larger factor tree. And this is really helpful when we have like big square roots, like the square root of, say, 120. Because if we have the square root of 120, the biggest perfect square that we can divide this by is, let's see, so we have 4 and 30. Looks like the biggest perfect square is going to be the square root of 4 and 30. 30 is not divisible by any perfect squares. So we don't have to simplify this any further. This is just 2, and so 2 and square root of 30. And this is done. Because if we make a larger factor tree and we do, well, this can be square root of 2 and square root of 15, and this can be square root of 3 and square root of 5. And even if we, say, didn't want to simplify that, and we have square root of 4, which can be broken up as square root of 2 and square root of 2, we have a pretty large factor tree here. We have square root of 2, square root of 2, square root of 2, square root of 3, square root of 5. And if we put all of those next to each other, square root of 2, square root of 2, square root of 2, square root of 3, square root of 5, we have to find all the pairs of square roots. The only pair we have here is 2. And then we have to multiply all of this stuff back together. So 2 times 3 times 5, 2 times 3 is 6, and 6 times 5 is 30. This is the square root of 30, and so we get back to the same answer we had before, 2 square root of 30, or we can just recognize that the biggest square root we can divide 120 by is, the biggest perfect square we can divide 120 by is 4, and since 30 isn't divisible by any perfect squares, we can bypass all of this, simplify this as 2, and then just 2 square root of 30. So it's a much simpler way if we do it this way. And so that's the method that I'm going to use for tackling the rest of these problems. So let's look at number 169. So for number 169, we have negative 2 square root of 6 plus 3 square root of 2 plus 2 square root of 6. The other thing that we wanted to use is that we can add and subtract radicals just like we would variables. So at first glance, it may not look very clear how we can do this, but what if we replace the square root of 6 with an x and the square root of 2 with a y? So instead, we can convert this into negative 2x plus 3y plus 2x. And it may be more clear how that we can actually tackle this. We have negative 2x plus 2x, which cancels, and all we're left with is 3y. But this was just the example using variables, so we don't actually want to have our final answer like this. We actually want to say that this is equal to 3. Like we said, we had square root of 2 was equal to y. 3 square root of 2. So we don't have to do variable substitution every time. In fact, we're probably not going to do this again in this video. But this is to make the point that we can add these things just like we would variables. And so this is just 3 square root of 2, because this negative 2 square root of 6 and this plus 2 square root of 6 cancel out. And so for number 169, this is our answer. For the next one, for 170, we have negative 2 square root of 5 minus the square root of 5 minus 3 square root of 5. And so this is to illustrate that same point again. If we think of the square root of 5 like it is a variable, we have negative 2 minus 1 minus 3. It doesn't actually matter what this thing is that we're multiplying by. It can be a square root of 5, it can be an x, a y, anything you want. But if we have negative 2 of them, we take one away, and we take away 3 more, negative 2 minus 1 minus 3 is negative 6 of whatever we are multiplying by. So in this case, we would have negative 6 square root of 5. And so this would be our final answer. So for number 171, what if we have negative 2 square root of 5 plus 2 square root of 6 plus 3 square root of 6? So we combine all of our like terms like we would with variables. We don't have any other things with square root of 5 because we have square root of 6 and the square root of 6 here. So we're stuck with this negative 2 square root of 5. However, we do have 2 square root of 6 plus 3 square root of 6. That combines as 2 plus 3, which is 5, square root of 6. And because these have different numbers under the radical, we can't combine this any further, and that's okay. We can have we can have an expression like this. It doesn't need to all simplify into one radical like the previous two problems. So over here, it was nice because these simplified into a single radical. However, it's okay if we have multiple radicals. For the next one, similar thing for 172, we have 2 square root of 2 minus square root of 3 plus 2 square root of 3. Well, the square root of 2 doesn't combine with anything else. There's no other things with square root of 2. And so we say that this is 2 square root of 2, and combine the negative square root of 3 and the positive 2 square root of 3. So negative 1 plus 2 is just 1. We don't need to write a 1, so it's just positive square root of 3. And again, this doesn't combine like the previous problem, and that's perfectly okay. So this is our final answer. So now we get into the harder problems where we actually have to take advantage of simplifying our square roots like we did up here before we got started with our first problems. So what if we have something that is like this with number 173, and we have negative 2 square root of 54 minus 2 square root of 6. Well, at first glance, we would say, well, this doesn't simplify any further because we have a square root of 54 and a square root of 6. So we're done, right? Actually not. Because the square root of 54 can be simplified with our by making a factor tree. So we think of the biggest perfect square that we can divide 54 by. And if you look at your chart, that's going to be 9. So 54 divided by 9 is 6. So the square root of 9 is 3, which means that the square root of 54 can actually be written as 3 square root of 6. And so now we can replace the square root of 54 with the square root of 6. So instead we have negative 2, 3 square root of 6 minus 2 square root of 6. And now we just have to multiply this 3 square root of 6 times negative 2. Fortunately, we just have to multiply these two numbers right here, the negative 2 and the 3, and we get negative 6 square root of 6. Bringing down this minus 2 square root of 6, we get negative 8 square root of 6. So, looking at the previous problems, we didn't check for that because I wanted to stress these properties over here that we can just add and subtract them. None of these actually simplify. 6, you can't divide it by a perfect square. Neither can you do 5 or 2 or 3. All of those are already simplified as much as they can be. However, for the ones that we're going to see for the remainder of this video, a lot of them can be simplified. We just have to ask ourselves, can this number be divided by a perfect square? And so in the case of 173, yes, 54 was divisible by 9. So square root of 9 was 3. That's how we were able to turn the square root of 54 into 3 square root of 6. So let's look at number 174. So for number 174, we have 2 square root of 45 minus the square root of 45. And sure enough, the square root of, 45 is divisible by a perfect square. So we can take the square root of 45 and we can break that up as the square root of 9 times the square root of 6. Now, because we divided by the biggest perfect square possible, 6 isn't divisible by a perfect square. So we just have to simplify the square root of 9 as 3, and we can write that as 3 square root of 6. Well, now we can replace square root of 45 with 3 square root of 6. So there's actually two different ways we can go about this. We can do that. We can replace the square root of 45 with 3 square root of 6. So 2, 3 square root of 6 minus 3 square root of 6. Do our multiplication. We have 2 times 3, which is 6 square root of 6, minus 3 square root of 6. And we end up with, we have 6 minus 3, which is 3 square root of 6. And we have this as our final answer. Alternatively, let's bring this party over here. The other way that we can do this is we can notice, well, this is in terms of square root of 45. If we do 2 square root of 5 and take one of those away, we just have 1 square root of 5 left over. Well, we've already determined that the square root of 45 is equal to 3 square root of 6. And would you look at that? That's the same answer we have over here. So clearly one of these ways was better. I do recommend, if you can, cancel out any roots, even if they're not simplified yet. Cancel them out first, and then simplify your square roots. But either approach you take, you'll end up with the same answer, so it doesn't really matter. It's just whichever way feels more comfortable to you. For the next one, we have for number 175, we have 3 square root of 27 plus 2 square root of 27. Well, like the previous problem, let's combine these first. We have 3 square roots of 27 plus 2 square roots of 27. We can combine this as 5 square root of 27. And the square root of 27 is divisible by a perfect square. So 27 can be broken up if we divide it by the biggest perfect square possible. It is the square root of 9 times the square root of 3. Well, square root of 9 is 3, so the square root of 27 is 3 square root of 3. Which means that we can rewrite this as 5 times 3 square root of 3. And when we do that, all we have to do now is just multiply 5 times 3, which is 15. And then we have our square root of 3 left over. And so this is our final answer. For number 176, we have negative 2 square root of 18 minus 3 square root of 8. So we can't combine these yet. So let's make factor trees. Square root of 18, biggest perfect square we can divide that by is 9. So we have square root of 9 times the square root of 2. The square root of 9 is 3. So we have 3 square root of 2. And the other one, square root of 8, the biggest perfect square we can divide that by is the square root of 4. The biggest perfect square we can divide that by is the square root of 4. And we have square root of 2 left over. We have a 2. So this is 2 square root of 2. So now we can replace square root of 18 and square root of 8 with 3 square root of 2 and 2 square root of 2 respectively. That gives us negative 2 times 3 square root of 2 minus 3 times 2 square root of 2. We multiply things together. We have negative 2 times 3, which is negative 6 square root of 2. And we have negative 3 times 2, which is also negative 6 square root of 2. And so, negative 6 square root of 2 minus 6 square root of 2, this is going to be negative 12 square root of 2. And so, this is our final answer. Okay, let's move on to, which one was that? That was number 176. So let's move on to number 177. So for number 177, we have negative 2 square root of 18 minus 2 square root of 8 minus 3 square root of 2. So again, we can break up square root of 18 as the square root of 9 times the square root of 2. The square root of 9 is 3, so this one is 3 square root of 2. For the square root of 8, we have square root of 4 times the square root of 2. So this is 2 square root of 2. And now we can replace square root of 18 and square root of 8 over here. And we have negative 2 times 3 square root of 2 minus 2 times 2 square root of 2. And then minus 3 square root of 2. We can multiply this negative 2 and 3 together. We have negative 6 square root of 2. Negative 2 times 2 is negative 4, so minus 4 square root of 2. And then minus 3 square root of 2. And combining all of this together, we have negative 6 minus 4, which is negative 10, and then minus 3, which is now negative 13 square root of 2. And so this is our final answer. For number 178, we have 2 square root of 54 minus square root of 24 minus 3 square root of 54. So we have square roots of 54 here, so let's just combine those. We have 2 minus 3, that's going to be negative 1, so just negative square root of 54. And then we have this minus square root of 24. So we've already made this a little bit easier for ourselves. And now let's just break up square root of 54 and square root of 24. So the biggest perfect square that 54 is divisible by is 9. And so our other number is 6. Well, square root of 9 is 3. So this is 3 square root of 6. And for the square root of 24, the biggest perfect square we can divide by is 4. So we have square root of 4 and square root of 6. And square root of 4 is 2. So this is 2 square root of 6. Which means we can now rewrite this as negative 3 square root of 6 minus 2 square root of 6. We have negative 3 square root of 6 minus 2 square root of 6. So negative 3 minus 2 is negative 5. And so we have negative 5 square root of 6. For number 179, we have negative square root of 8 plus 3 square root of 8 minus square root of 27. So first, let's just combine these square roots of 8. We have negative 1 plus 3. So we're going to have 2 square root of 8 minus square root of 27. Square root of 8, as we've seen before, can be broken up as square root of 2. Square root of 4, square root of 2. So 2 square root of 2. And then square root of 27 can be broken up as square root of 9 square root of 3, which is 3 square root of 3. Replacing square root of 8 and square root of 27, we get 2 times 2 square root of 2. Minus 3 square root of 3. We multiply 2 and 2 together. So we get 4 square root of 2. And then minus 3 square root of 3. And now, because we have square root of 2 and square root of 3, we already simplified these as much as we can. We can't combine these any further, and that's okay. So our final answer is 4 square root of 2 minus 3 square root of 3. And that's our final answer. And for the last one for this one, we have number 180. And that one is 2 square root of 6 minus 2 square root of 54 minus 2 square root of 18. So for this one, we have the square root of 6 can't be simplified anymore, but the square root of 54 and square root of 18 can. So the square root of 54 is, we have these, dividing that by the biggest perfect square possible, that is 9. That's going to be broken up as the square root of 9 times the square root of 6. Square root of 9 is 3. And so we have 3 square root of 6. The square root of 18 can be broken up as the square root of 9 times the square root of 2. Well, square root of 9 is 3, and we have 3 square root of 2. So now, we can rewrite this as 2 square root of 6 minus 2 times 3 square root of 6 minus 2 times 3 square root of 2. Now we have 2 square root of 6. Negative 2 times 3 is negative 6, so minus 6 square root of 6. And negative 2 times 3 is negative 6, so minus 6 square root of 2. We combine our square roots of 6. We have 2 of those, and we're taking away 6. This gives us negative 4 square root of 6. And then taking away 6 square root of 2. We can't simplify these any further, and so we're left with this. And this is our final answer. So I'm actually going to break this video up into 2 parts because this one's already 27 minutes long. And so I'll have another part 2 for questions 181 through 192. So I'll see you then. Thank you for watching.